Quantum mechanics is a field that is developing rapidly. But what practical difference does quantum theory make to our daily lives? Professor Lu Zhou Shum from the Department of Physics at the University of California, San Diego, presented a lecture at the Open University of Hong Kong explaining the basics of quantum theory and its applications. Through practical illustrations from the worlds of cryptography, photography, medicine, and computer games, among other areas, Professor Shum demonstrated the revolutionary impact of quantum mechanics on technological development and how future research in this area has the potential to improve our lives.
I want to make 3 points in this talk. The first one is just to give you a sense of what is it that quantum mechanics or quantum theory is so unusual. It was designed at the starting from the beginning of the 20th century, last century, to explain small things, basically light and electrons to start with, and then about atoms, how atoms is built. But of course, it should apply to big systems. But you know, a century later, we're still working on what does it mean for the big systems. But I thought it would be interesting to try to talk about it in terms of how it would impact our lives in the maybe next 50 years. So the first thing, of course, you thought about, well, it's physics, it's engineering, therefore it must be technology. Okay, so what is it that this is going to promise us? I say promises. Actually, there's some things there's some quantum engineering things that already you can buy. You can go online and so it is commercialized already. The other thing is culture. Now, I don't want to talk about culture in general, but there is one thing that is somewhat puzzling, we're still struggling with. Everybody has a different way of trying to explain it. And so what I want to do is to focus it as a sense of reality. So I want to explain that. The first thing about quantum mechanics is that it describes a state. Now, what do you mean by a state? Let me take a coin. If you tossed it up in the air and let it land on the table, it would land either head or tail. You cannot predict it. We describe the state on the table. It would be either head or tail. H or T for short. So this is the classical physics description. We call it classical, meaning the physics that we had, the science that we had before 1900. To describe the state of the coin in the air, in principle, we should be able to, just before you flip the coin, in principle, you know the initial condition. So if you flip it, where everybody agrees, in principle, according to Newton's law, we should be able to see, to predict how it would flip and then come down and which way it would land. But because we don't know the initial condition, we don't know the air, the effect of the air, so if you do the experiment, there's a 50-50 chance, unless the guy who flipped the coin is an expert gambler, it would have 50-50 chance of having head or tail when it lands. So the reason we use probability is because we don't know the condition under which it's done. It's not because we don't know the laws of physics. In principle, we should be able to predict it perfectly. Okay? This is not quite true, but that's not what I want to talk about. So we would accept the fact that We cannot say exactly which way it would land because we are missing some knowledge. So we all accept the fact that we can use probability, which we would describe how this would land. That's called the state. Now, in quantum theory, there are similarities and there are differences. And the similarities are striking, but we live in the classical world. But this describes, of course, not the big coin, but a tiny little thing which I will produce that might have a property. The property might have two values, if you like. One is correspond to at the head of a coin. The other correspond to the tail of a coin. I'll give you an example later for the electron. Then what we say is mathematically, when it's in the air, it actually can be a combination of two possibilities with a very definite mathematical representation of a number times this possibility, which we call heads. So if I have a quantum coin, it would have the possibility of, a number times this, another number times this. And so it is sometimes called wave theory because we can't think of a coin that would add. So in our experience, what are the things that you can add? Well, wave, if I put in a wave like this and I put another wave, then the amplitude will go up, right? Or they will cancel each other. So that's a good description. But what I find is that we don't actually know a whole lot about waves, even in daily experience. So as a teaching tool, it's actually a very bad idea because then it started solving, the first day you ask the student, do you know how to solve the wave equation? The whole thing just goes downward from there if you don't know how to solve the wave equations. But there is actually another quantity which is very good and which we actually have some intuition about. That's a vector. Now, if you think of this as two different vectors, you go on the map, you think of this one as pointing east, and the tail is pointing north. You have two different directions, right? And so you can have a combination of directions because if I go east for a mile and then go north for a mile, it's the same as if I go 45 degrees. So if I go 45 degrees vector, it has an equal component of the two. Hey, that's a description of the coin. But what does that coefficient mean? The coefficient is the probability. Now, this is a very quantum mechanical statement. This tells you that in this mixture, if I square this number and I square it, for those who know mathematics, actually I'm using complex numbers, and then the absolute value, of course, probability has to be real. But minor details. Today, I don't want to worry about minor mathematical details because there's these major physical ideas you have to try to grasp, which is that this is a definite combination, and we have an equation called the Schrödinger equation for it to solve, just like the Newton's law. But when you finish, you're going to get two numbers which are the probabilities for this state and this